Usually galvanometers are used to detect very small currents. Very small means they'll be in the range of milliamperes. Fine. The range will be mentioned on the instrument. Just a moment. I'll show you the diagram of a galvanometer. Not diagram, picture of a galvanometer. Right. So you just need to connect the current wires to the galvanometer. You'll be doing this experiment also in your 12th class. You're in 12th only, no? Right. And you can see that the needle of the galvanometer, okay, in this diagram it is pointed at 0 because it's not connected to anything. If you connect the wires based on the current flowing, the needle can deflect this way and also this way. So a galvanometer can even tell you in which direction the current is flowing. Fine. And this 100, 200, 300 that you see would be milliamperes. Okay, so that is the, like for this galvanometer, you can say that the range is 300 milliampere. Okay, that's the maximum current that it can show. This is also called the full scale deflection current of the galvanometer. Okay, at full deflection, the current that it can indicate is 300 milliampere, not more than that. Okay, now can any of you tell me what would happen to the galvanometer if we pass a current of more than 300 milliamperes in this case? Depending on the current we pass, the magnetic field produces a torque, and depending on the torque, it rotates, the needle rotates. Okay. What will happen if we pass a current of more than 300 milliampere through this galvanometer?
So the reading will be stuck at 300.
That's all. See, there will be additional torque generated on the coil. Okay. But there will be a mechanical stopper at the end of the scale. Like there will be one small stopper here and one small stopper on this side also. It won't allow the needle to go beyond that. Fine. So torque is being produced, but we are not allowing the coil to rotate any further. It will be mechanically restricted to not rotate beyond a certain angle. Fine. So that maximum current that the galvanometer can indicate is called its full scale deflection current. Okay. Usually it will be in milliamperes itself. But see, sometimes it will be necessary, not sometimes, many times it will be necessary to measure currents much greater than 300 milliamperes. Fine. In such situations, we use an instrument called ammeter. Ammeter is also a device used to measure current. It measures larger currents than what a common galvanometer does. Okay. Now, how to convert galvanometer to ammeter? Let us discuss that. See, when current passes through a galvanometer, it will tell you how much current is passing through it. Okay. But it can only indicate limited current. We need to increase the range of the instrument. Or based on the current indicated by the galvanometer, we should be able to predict a greater amount of, we should be able to calculate a greater amount of current passing through the wire. That is the aim. Okay. So let's say this is the wire in which a galvanometer is connected. What is present inside a galvanometer? Anyone? Or what all are present inside a galvanometer?
Magnets and coils.
There is a permanent magnet and there is a coil, right? In fact, we discussed something called current sensitivity of a galvanometer, d theta by di. Theta is NAB by K into I, then d theta by di, current sensitivity of a galvanometer, is NAB by K. Do we want a galvanometer to have high current sensitivity or low current sensitivity?
Low current sensitivity.
Why? Define current sensitivity, not the formula. What do you understand by it? Okay, anyone? What do you understand by current sensitivity of a galvanometer?
Sir, it is like the ability to measure the current precisely.
Kind of. Okay. So basically,
Like it depends on how much charge it has and how much it deflects the needle. Like how
much
much current
current?
passes and how much it
Okay.
deflects.
Okay, I got one answer in chat is ability to detect the change in current. Correct. Okay. So basically, how much it deflects per unit current. That is what is current sensitivity of a galvanometer. And we want the galvanometer to be to have very high current sensitivity. Even for small currents, it should show large deflection. Okay, that is the purpose of a galvanometer. So we intentionally make galvanometers with high current sensitivity. And one way to increase the current sensitivity of a galvanometer is to increase the number of loops, okay, in the coil of the galvanometer. So a galvanometer has a tightly wound coil inside it with a large number of loops. So there is a significant amount of wire inside the galvanometer, okay, significant length of wire inside the galvanometer. And because there is a significant length of wire inside it, when current passes through the galvanometer, it will offer a significant amount of resistance as well. Okay, can one of you quickly tell me how resistance of a conductor depends on its length?
So resistance will be rho L by A. Rho
R
into
is
L by A.
equal to rho L by A, correct. So greater the length of the coil, length of the wire inside the galvanometer, okay, greater the resistance. Okay, someone said directly proportional, correct. If resistivity and area of cross section are uniform, then it is directly proportional, correct. So remember, galvanometers have significant resistance. Okay, so when current passes through the galvanometer, it has to overcome that resistance also. So that resistance gets added in that wire or in that network. Fine. Now assume a current I is flowing in this wire and the galvanometer can read a maximum current of Ig, not more than that. Okay, so Ig is the full scale current, deflection current of the galvanometer. Now what will happen when I is greater than Ig? The galvanometer will be stuck at Ig. It cannot indicate values more than that. Okay, but we now want an instrument which can indicate values more than Ig also. So what we do is we divert some of this current through another resistance. And as you can see, this other resistance is connected in parallel with the galvanometer. Okay, this extra resistance that we use is called the shunt resistance. So what happens when the current I enters at this junction? Some current goes through the galvanometer, remaining current goes through the shunt resistance. Okay, let's call current going through the galvanometer as Ig. Then how much will the remaining current be? Out of the current I, if Ig continues straight, how much will be the diverted current?
I minus Ig.
I minus Ig, correct. Fine. And which current do we want to measure? Do we want to measure Ig or I minus Ig? Which is the current we are interested in? The actual current in the wire, that is I. Okay. Now we know that, like we can see that this resistance Rs is connected in parallel with the galvanometer. So Rg, Rs are in parallel. When two resistors are in parallel, what do they have in common? Which quantity will be common for them? When two resistors are connected in parallel, which quantity will be common?
Potential difference.
Potential difference. The voltage will be equal for them, across them. Okay, so you can say that potential difference across the resistance of the galvanometer should be equal to potential difference across the shunt resistance. And how do we express potential difference across a resistor? Current multiplied with the resistance. So Ig Rg should be equal to I minus Ig Rs. Simple calculation. So we can say Ig into Rg plus Rs is equal to I Rs, and from that we can estimate the current I as Ig, current in the galvanometer, into 1 plus Rg by Rs. So if you know the reading of the galvanometer, that is Ig, you can tell what is the original current in the wire I. So this is how an ammeter works. Basically, ammeter consists a galvanometer along with some extra resistance called a shunt resistance. So this whole box is what you call an ammeter. Fine. Is the idea clear to all of you? Current I flows into the ammeter box. Inside the ammeter box, it gets diverted. It gets split into two paths, split along two paths. One path leads through the galvanometer, the other is through the shunt resistance. Fine. Based on the current shown by the galvanometer, we can estimate what is the original current I flowing in the wire. Okay, so I is equal to Ig into 1 plus Rg by Rs. So some basic questions based on this can be asked. Like they can tell you that a galvanometer can measure so and so current. How much shunt resistance should be connected in parallel so that we can make an ammeter? Let's try one question like that. Let's say full scale current of a galvanometer is let's say 200 milliampere, and its resistance is some 20 ohms. What is the shunt resistance required to convert it into an ammeter having a range of, okay, let's say 20 ampere. 20 ampere is too much actually. Let's take 5 ampere. Okay. Solve this quickly. Type your answers in chat, all of you. Yes, you have any doubt?
Yes, sir.
Okay, we'll discuss after this problem. If it is about this problem, you can ask.
No, sir, about the
Okay.
topic.
Okay. Why is it taking so long? If you get answer as some ratio, just type the ratio. You don't need the exact decimal value. I got one answer as 25 by 6. That is 4.1 something, 4.15. We'll see. I got another answer as 125 by 6. Okay. Fine, let's see. See, we know what maximum current the galvanometer can measure, and we need to find out how much shunt resistance is needed to make it an ammeter with a range of 5 ampere. I got one answer as 5/6. We'll discuss. So it's a direct application of this formula. I basically is the current which the ammeter would indicate. Okay. We want the ammeter to be able to indicate a current of up to 5 ampere. So when galvanometer has full scale current passing through it, ammeter should have 5 ampere passing through it. I mean, ammeter should indicate 5 ampere. So 5 is equal to Ig. Full scale deflection of galvanometer is 200 milliampere. So 200 into 10 power minus 3. Because 5 is in amperes, this side also you have to take amperes only. Okay, so you can't just write 200 and leave it like that. 1 plus Rg by Rs, 20 divided by Rs. Okay. So 200 into 10 power minus 3, that's like 200 divided by 1000. 200 divided by 1000 is 1 by 5. Send the 5 that side. You get 25 is equal to 1 plus 20 by Rs. So 20 by Rs becomes 25 minus 1, 24. So Rs becomes 20 divided by 24. 5/6 is correct. How did some of you get other answers? What mistake did you make, or did I make any mistake? Tell me what mistakes you made. I think this solution is fine.
No, so 5/6 is correct.
What mistake you made?
Like I took it as 4, like multiple of 4, and I did some.
Okay, fine. Pradyun, which part do you want me to scroll up to? Is this enough? Okay. We want the ammeter to show a maximum current of 5 ampere. When will the ammeter show maximum current? When the galvanometer is showing its maximum current. Okay. So current shown by the ammeter should be 5. Galvanometer at that instant, galvanometer should be showing 200 milli. Milli is 10 power minus. That is important. Otherwise, you will not get the correct answers. Okay. Now see, suppose there is a circuit. Let's consider a basic circuit. Simple DC circuit. Let's say there is a DC voltage V, battery of resistance R. Sorry, resistor of resistance R. How much current should be flowing in this? How much is the current flowing in this loop?
V by R.
I is equal to V by R. Yes, just a moment, we'll discuss. Okay. Now, suppose you want to check whether this much current is actually flowing or not. What you will do, you will have to connect the ammeter in series with that wire. In whichever wire you want to measure the current, you have to connect the ammeter in series with that wire. Okay. So you connect the ammeter here. But the moment you connect an ammeter, what happens? Ammeter has some resistance in it. Okay, it consists of galvanometer and a shunt resistance. Effectively, the ammeter will have some resistance. Now tell me, the connection of ammeter, like after connecting the ammeter, will this current get disturbed or will it still be V by R? When you place the ammeter in the circuit, will the current still be V by R or will it get disturbed?
If it's an ideal ammeter, it should be V.
Not ideal. See, we are discussing real cases only.
Slightly.
It should be very negligible.
Okay, it will be disturbed, that much we can say, right? Just a moment. Okay. So you are increasing by connecting the ammeter, you are increasing the effective resistance of that wire. Okay, so current will decrease a little bit. But we want to, as one of you said, it should be minimized. Okay, we have to reduce that disturbance cost to the current. How can we do that? By reducing the resistance of the ammeter. Okay. Now, ammeter has a galvanometer and a shunt resistance in it. Can one of you tell me how much will be the effective resistance of the ammeter? It's like there are two resistors in parallel, RG and RS. What will the effective resistance be?
RGRS by RG plus 1.
For two resistors in parallel, you can use R1, R2 by R1 plus R2. So RG, RS by RG plus RS. They can ask you questions like this also. Fine. That's the resistance of the ammeter. We want to minimize this. Now we can't disturb the galvanometer. The galvanometer's resistance depends on the number of turns, number of loops that it has. Okay, and we want it to be a sensitive device, so it will have those number of loops and all. Okay. Now, how to minimize this? If you take RS to the denominator, plus 1, you can write it like this. You can, when you are constructing the ammeter, you have the choice to change RS value. You can fix whichever value of RS you want. Okay. So to minimize the overall resistance of the ammeter, tell me, should RS be high? Should the shunt resistance be high or low? Based on this expression, you tell.
Low.
Low. Okay. See, if shunt resistance is decreased, basically this term will increase, but that term is in the denominator. So as a whole, the resistance will decrease. Okay. So in order to reduce the overall resistance offered by the ammeter, you will use a small value of shunt resistance. That is one advantage that a small shunt resistance gives. Okay. So RS should be a small resistance compared to RG. Okay, why? We can decrease the overall resistance of the ammeter. There is another advantage also. If you take a small value of shunt resistance, okay, it's in the denominator here. Basically, what it leads to is a high range of the ammeter. Okay, because RS is in the denominator, smaller that value, greater will be the range of the ammeter. Okay, because if the shunt resistance is low, most of the current I will follow this path. Only a small value or only a small current will go through the galvanometer. That's the idea. Okay, when there are two parallel paths, more current will flow in the path which has less resistance. So if you decrease the shunt resistance to smaller and smaller values, greater and greater current will go through the shunt. Small current will go through the galvanometer. Okay, so by decreasing the shunt resistance, you can increase the range of the ammeter also. So there are two advantages. First, resistance of the ammeter will decrease or will be low, and the range of the ammeter will be high. Okay. So when converting a galvanometer to an ammeter, remember we connect a shunt resistance in parallel, and smaller the value of that shunt resistance, the better. Okay. Yash, what is your doubt?
Sir, can you scroll a bit up?
How much?
Like, yeah, this one, sir. Sir, here we said that di by d theta is NAB by K, sir.
D theta by di is NAB by K.
We can say that NIB, like torque acting, is equals to K into theta.
Wherever the needle settles, the torque produced by the magnetic field is balanced by the torque produced by the torsional spring.
Sir, and K here is the stiffness, right, of the spring here.
We should not call it stiffness. Stiffness is spring constant. This is torsional constant. It is dimensionally different.
So, is there a way, if we manipulate this, we can convert it into like a galvanometer to ammeter?
See, we can. That can be done. Basically, by decreasing the sensitivity, you can make it an ammeter directly. Okay. See, galvanometer, what it does is, for small currents also, it rotates by a large angle. Okay. Because the spring allows it to rotate. As you said, by increasing the stiffness of the spring, okay, don't actually call it stiffness, by increasing the torsional constant of the spring, yeah, you can prevent it from rotating so much for small currents. Can be done. Okay, directly by
Yes,
making
sir.
changes in the instrument, you can. Yes.
Okay.
But we usually don't do that. We don't open a galvanometer, change its stiffness and all. We add an extra resistance, make it an ammeter. Okay. Next, we can even convert a galvanometer into a voltmeter. What does a voltmeter do? What does a voltmeter do?
Where it measures the voltage.
Measures the voltage or the potential difference between the 2 points at which you connect its terminals. Okay. Now, galvanometer can indicate current passing through it. As such, it can indicate how much current passes through it. And we know the resistance of the galvanometer. Usually on the device, it will be mentioned. When you know current and resistance, you can tell what is the potential difference. Okay. So, for example, suppose there's a galvanometer whose resistance is Rg, having a current Ig flowing through it. Okay. So, we can directly tell that the potential difference across this galvanometer must be Ig into Rg. So depending on the current measured by the galvanometer, we can tell the potential difference also. So a galvanometer can directly be used to measure potential differences. But because this Ig value, okay, the current measured by the galvanometer is usually small, the whole potential difference that it measures will also be small. Okay, so it won't act as a voltmeter of significant range. The range will be low. What I mean is, suppose there is a circuit like this. Let's say there are two resistors R and 2R. Connected to battery of EMF V. We are considering ideal battery or ideal cell. Okay, let's say its EMF is V. Tell me, what will be the potential difference across the resistance R? What or how much will the potential difference across R be?
V by 3.
Pradyun, I'll take your doubt after this. I got one answer as V by 3. That is correct. I don't know why you all are taking so much time to solve this. Resistors are in series. They'll have the same current passing through them. If current is same, then voltages will be in the ratio of resistances. So the voltage V that is applied across this branch will have to get split in the ratio 1:2. So the first one will get V by 3, second one will get 2V by 3. Let it be. Suppose you want to verify this. What you can do is you can connect the galvanometer directly in parallel with the resistance because you want to measure the voltage across that resistor. So based on the current passing through the galvanometer, it will tell you what is the potential difference across these 2 points. Okay, across let's say A and B. Galvanometer can tell you what is the potential difference between A and B. Same is the potential difference between X and Y. That's the potential difference we want to measure. So you can use a galvanometer directly, but the range will be very small. Okay, so we need to convert it into an instrument which has a higher range for the potential, okay, or potential difference that it can measure. So for that, what we do is we connect the galvanometer, or to the galvanometer, we connect an extra resistance, this time in series. So galvanometer has its own resistance Rg. Now we connect the extra resistance Rs like this. Galvanometer along with that extra resistance in series together is called a voltmeter. Okay. Now suppose a current I flows through it, or let's call the current as Ig itself. Across the galvanometer, the potential difference is Ig, Rg, and across this resistance, the potential difference will be Ig into Rs. Since they are in series, the same current passes through both of them. Then the total potential difference across this combination will be Ig into Rg plus Rs. Okay. And that will be the reading indicated by the voltmeter. I can say delta V is equal to Ig into Rg plus Rs. So now that Rs is getting added, the range of the voltmeter increases. Okay. And higher the value of Rs, higher the value of shunt resistance, higher will be the range of the voltmeter. Okay. So when converting a galvanometer to a voltmeter, we connect the shunt resistance in series with the device. Okay. And higher the shunt resistance, greater will be the range of the voltmeter. There is another advantage also. Now see what we are doing. When you want to measure the voltage, what you do is you connect the voltmeter in parallel with the, like in this case, the voltmeter is connected in parallel with the resistance across which you want to calculate the or measure the potential difference. Now what will happen when you connect a voltmeter like this? The original current flowing in this loop, okay, let's call it I, gets disturbed. Now some current will have to flow through the voltmeter, only the remaining current will flow through the resistance. Okay, so we are disturbing the current flowing through that resistance originally by placing this voltmeter. Now we want to minimize that disturbance. To minimize the disturbance, the current passing through the voltmeter should be low. Okay, we need to decrease that as much as possible. And taking a high shunt resistance is a way of doing that. If you use a high value of shunt resistance, tell me what is the effective resistance of the voltmeter? Okay, you can directly see it is Rg plus Rs. Okay, so by using a large shunt resistance, you can increase the resistance of the voltmeter, and if you do that, the current getting diverted into the voltmeter will be as low as possible, will get decreased. Okay, so most of the current flowing in the original branch will stay in that branch. Okay, so the disturbance to the current can be minimized by using a high value of shunt resistance. So when converting a galvanometer to a voltmeter, shunt resistance should be high. And as I said, there are two advantages. First is it increases the range of the voltmeter. The other advantage is it increases the resistance of the voltmeter such that the original current in the circuit is not disturbed much. Okay. So any doubts in this? How to convert galvanometer to voltmeter, how to calculate its range and all? Right. So how much ever you increase the resistance, a little bit of current will have to pass through the voltmeter anyway. So some disturbance will definitely be there. And the reading that you get from a voltmeter will definitely be less than the actual potential difference that was supposed to be measured. So both ammeter and voltmeter, they will give you readings which are slightly less than the actual values. We can minimize the disturbance, but we can't make it zero completely. Okay. Fine, that is all there is in this chapter. We started with Biot-Savart law. Okay. It helps us calculate the magnetic field produced by a current. Then we discussed its applications. Okay, straight wire, circular arc, full circle at its center, full circle on its axis. Then we talked about magnetic dipole. Okay, magnetic dipole moment. Then we discussed Ampere's law. Okay, application of Ampere's law, how closed integral B dot dl will sometimes be plus mu naught I, sometimes it will be minus mu naught I also. Okay, it depends on how you are moving along the closed path. After that, what did we talk about? I think force exerted by a magnetic field on a charge, F is equal to QV cross B. And different cases of that, different cases of motion of charge in a magnetic field. Then combined electric and magnetic field Lorentz force. Then based on that, we discussed about a velocity selector. After that, force acting on a current wire, IDL cross B. That's the force acting on a current element. If you want total force, it is integral IDL cross B, which for a uniform field becomes IL cross B. Next, we discussed torque. Torque is equal to NIA cross B. Yeah, followed by galvanometer and whatever we discussed today. Fine. Let's solve some problems. First, derive the dimensional formula of mu naught. Make this fast, all of you. Mu naught and magnetic field also, both. Okay. The dimensional formula should not take this long. Tell me which equation or formula can be used to get the dimensional formula of magnetic field.
Sir, force on a current carrying element, like F is equals to BI.
You can use F is equal to ILB, you can use F is equal to QEB, any one of them. See, if you want to derive dimensional formula of any quantity, you think of a formula which involves that quantity. Okay. And if you know the dimensions of the other terms in that formula, then you can tell the dimension of this quantity, dimensional formula of this quantity. So let's use F is equal to QVB. Then dimensionally, magnetic field will be dimensions of force divided by dimensions of charge multiplied with speed, velocity, whatever it is. Force is ml t power minus 2 divided by charge. Isha, what is the dimensional formula of charge? No response. Okay. Charge current into time. You can write it as IT or AT. And speed LT power minus 1. That's all. Simplify it. You'll get the dimensional formula for magnetic field. Okay, let us write it. M will be there. L in the numerator, L in the denominator gets cancelled. T power minus 1 cancel. So M A power minus 1 T power minus 2. That's the dimensional formula of magnetic field. I think we had done this in one of the previous classes. Okay. The next thing we need to derive is the dimensional formula of mu naught. How to do that? Which formula shall we use? As far as we have seen, mu naught appears only in the formulas of magnetic fields. Okay. So you can use any one of the magnetic field formula which you are comfortable with. Now that you know the dimensions of magnetic field, you can use that to get the dimensions of mu naught. So tell me, which formula of magnetic field shall we use to easily get the dimensions of mu naught? Okay, Manasa, can you tell that magnetic field produced by any geometry, straight wire or circle at its center, arc at the center, anyone? Solenoid inside it.
So for circular coil, mu naught I by 4 pi r. Phi mu naught I by 4 pi r.
No, tell the formula first. B is equal to?
Surface integral of mu naught I by 4 pi r.
Integral of mu naught I by 4 pi r. Why will that?
For long solenoid, we can take mu naught ni also.
Solenoid we can use mu naught ni, that's fine. Okay, but other formulas also, you be clear with the formula, okay? So she's saying we'll use the formula of magnetic field of a solenoid, mu naught ni, long solenoid. Okay. Our aim is to get the dimensions of mu naught. So we can say dimensional formula for mu naught is dimensions of magnetic field divided by dimensions of n multiplied with dimensions of I. Okay. Magnetic field we just derived m a power minus 1 t power minus 2. Fine. Can one of you tell me the dimensional formula for n in mu naught ni?
Sir, it's dimensions.
Okay. Do you all agree with that? N is dimensionless. Can one of you
Yes,
tell me
sir.
what it means? The answer is no, n is not dimensionless. It has dimensions. One of you tell me what is the meaning of n in this formula?
Number of terms per unit.
Number of turns per unit length. So basically, small n would be capital N, which is a number, divided by the length of the solenoid. Number won't have dimensions, but length will have. Okay. So small n's dimension is L to the power of minus 1 per unit length. Okay. Number per unit length. That's a common mistake that most students make. It is L power minus 1. If you want, we'll verify this with another formula of magnetic field also. And I is current, so we'll write it as A. Therefore, mu naught dimensions become M. A goes to numerator, A power minus 2. L goes to the numerator, L t power minus 2. That is the dimensional formula for mu naught. Okay, let's use another formula for magnetic field to check whether the dimensions of mu naught we got is correct or not. Yash is saying for a loop it is mu naught I by 2r, correct. For loop at its center, circular loop at its center, we know magnetic field is mu naught I by 2r. Let us use this. So dimensions of mu naught according to this should be dimensions of magnetic field multiplied with dimensions of r, that is the radius, divided by current. I think this is enough to check. In the previous derivation also, we had magnetic field in the numerator, current in the denominator. Here also we have magnetic field, current. There we had n in the denominator. N is inverse of length. Here we directly have radius in the numerator, that is length. It's the same thing. This inverse of length, L goes to numerator. It gets multiplied there. Okay. So remember, n is number of turns per unit length. It has dimensions. It's not just a number. Okay. Next. One of you quickly tell me, what is the formula for radius of circular motion of a charge in a magnetic field when velocity is perpendicular to it?
MV by Q.
mv by qb, provided the magnetic field is uniform. Okay. Solve this quickly, all of you. I got one question, whether it is positively charged or negatively charged. You are probably talking about the sulfur ion. How do you think it matters?
So like if it's a cation, so like it
Hmm.
will have a positive charge, no? And if it's anion, it will have negative charge.
Okay, how does it matter in calculation of the radius?
So like on charge we have Q, right? So
There you will substitute negative if charge is negative. Then radius becomes
no, so
negative.
like alpha particle, it is having positive electrons. Like sorry, two electrons. No.
Alpha particle doesn't have electrons. It has protons, neutrons.
Sorry, two protons, two protons. So
Let it
here
have.
in sulfur,
I didn't understand still. How does whether sulfur ion is positively charged or negatively charged, how do you think it affects the answer? Like,
So
see,
what typically charge?
just a moment, just a moment. They said singly charged sulfur ion. Single charge means one electron should either have been added to it or removed from it. Yes, you tell me, if you add one electron to a neutral sulfur atom, what will its net charge become if you add one electron to an atom?
it will become negatively charged.
How much?
1 is
Tell the charge of electron. No?
1.6 into 10 power minus 19.
Minus 1.6
Minus
into 10 power
1.6.
minus 19 coulombs. Okay. Suppose you remove one electron. How much charge would it be left? How much would be the net charge on it?
1.6 into 10 power.
Either way, it's the same magnitude. No, then how does it matter for the answer? Whether
So
it is
means
positive.
like here we have to just take the magnitude.
How can
for
you
the
make
radius.
radius negative? By taking charge along with the sign,
Oh, yeah.
radius will become negative. Does
Got
negative
it.
radius? See, one intelligent question to ask would have been, sir, adding electron and removing electron gives different masses. Okay, to a sulfur atom, if you add an electron, mass will increase. If you remove electron, mass would decrease. Then maybe, I mean, at least on that basis, if you had asked, it would have been more valid. But still, adding electron or removing electron won't cause significant change in the mass of a sulfur atom, because, can one of you explain why?
Mass
So
on
like mass of an electron is nearly negligible.
Mass of electron is negligible compared to protons and neutrons. Okay, and sulfur, I think it has 16 protons, right? Sulfur atomic number is 16 only, no? One of you tell me, I don't remember.
Yes.
So it has 16 protons and 16 neutrons also. They said mass is 32 AMU. So there must have been 16 protons, 16 neutrons compared to the mass of 16 protons and 16 neutrons. And there would already be 16 electrons also. So it doesn't matter whether you remove an electron or add one electron. There is already a lot of mass present in it. The mass that you are adding or removing is negligible. Okay. Solve it now, all of you. Someone else was asking me something. Rishi, I think.
No, sir, I don't ask.
Okay, if any of you has any other doubt, you can ask. Otherwise, solve it quickly. Why is it taking so long? Yash, where are you stuck?
No, sir, I'm doing, sir. I'm at the last part.
Okay. Shashank.
I'm almost done.
Okay, do it, all of you. I got one answer as 4:1. We'll see. Okay, listen, all of you. They said they are initially at rest and they are accelerated through a potential V, means they are both accelerated through the same potential. Now in R is equal to mv by qb, V is not the potential, V is the speed with which the charge moves. Okay. For potential, just to avoid confusion, let's use capital V. and then allowed to pass into a region of uniform magnetic field which is normal to the velocities of the particles. Within this region, we need the ratio of radii in which they move. Okay. So Rs to R alpha, it would be mass of the sulfur ion, speed of the sulfur ion divided by charge on the sulfur ion magnetic field, mv by qb, mass of alpha particle, speed of alpha particle divided by charge of alpha particle magnetic field. They are both in the same magnetic field, so B will get cancelled. Mass ratio is given in the problem 32:4. That's like 8:1. Charge ratio, sulfur to alpha particle. Sulfur is singly charged, so 1. Alpha particle charge is 2. It has 2 protons, so 2e. So charge ratio will be 1:2. We need the speed ratio. Speed ratio is not directly given in the question. They said it is accelerated through the same potential. Can one of you tell me, when a charge q is accelerated through a potential difference V, what happens? Or what can we say based on that?
The kinetic energy acquired by each particle is equal to the potential difference.
Each charge, the charge q will gain a kinetic energy of qv, okay, provided it starts from rest. Okay, not provided. Yeah, provided it starts from rest, it gains a kinetic energy of qv. So you can say kinetic energy of the sulfur ion is charge on the sulfur ion, that is E, multiplied with the potential difference that it goes through, that is V. Okay. And kinetic energy gained by the alpha particle is charge on the alpha particle 2e multiplied with the potential difference that it goes through. Okay, so we know the kinetic energy ratio, and we can write that as half mass of sulfur ion, speed of the sulfur ion squared, and this is half mass of alpha particle, speed of alpha particle squared. By dividing these two, you can get the ratio of speed of sulfur ion to the speed of alpha particle. Left hand side, the ratio is 1/2. Half will get cancelled. Mass of sulfur to mass of alpha particle is 32:4, that is 8:1. And Vs square divided by V alpha square. So Vs square by V alpha square would be 1/16, which means Vs by V alpha is 1/4. You can substitute that. 1 here, 4 here, then the answer becomes, okay, 2, 4 cancel, you'll be left with 8:2, that is 4:1. Okay, you need to, like I told you many times already, this is very important. When a charge q goes through a potential difference, it can gain an energy of qv or it can lose an energy of qv. But if it is starting from rest, only gaining can happen, losing cannot happen. Okay, it gains a kinetic energy of qv. Right. Next, think of this, all of you. Suppose there are two circular loops. They are both on the, they both have their centers on the x-axis. They are both in the YZ plane. This is one loop, and at a large distance from it, there is another loop also. What does a current carrying loop behave as?
Magnetic line.
Magnetic dipole. So effectively, these are two magnetic dipoles. Okay. Let's say both have a radius r. Separation between them, let's call it x. X is much greater than r. Okay. And let's say both of them carry currents I in the same sense. Let's call the loops as L1 and L2. Tell me, will L2 experience a force due to L1? If yes, in which direction? Think carefully and answer. I'll give you 2 minutes. Will L2 experience a net force due to L1? If yes, in which direction? Any answer? Okay, listen. If at all they exert any force on each other, what kind of force could it be? What kind of force can it be?
Magnetic
Yes, your voice is
force
breaking.
due to magnetic field.
Okay, magnetic force. One of them creates a magnetic field. The other one is in the presence of that magnetic field, so it can experience a force due to that. Let's see. Tell me, the loop L1, you can see how the current is flowing in it. Half the loop is out of your screen, half the loop is behind. And in the part out of your screen, the current is going up. So it's like this. Okay, curl your right hand fingers along the flow of current. What is the direction of magnetic field produced by L1 at the position of L2? Direction of magnetic field produced by L1 near L2. The chapter is complete and you don't know how to tell the direction of magnetic field.
So into the screens.
Why will it be into the screen, sir? It's a current carrying loop. L1 is a current carrying loop.
Left to
Yeah. Towards it, sir. Right, towards L1.
You'll have to curl your right hand fingers along the flow of current in that loop. Correct. It will be towards the loop. So on its axis, exactly on its axis, the field will be this way. This is the field produced by the first loop. Fine. And since the distance is large, slightly off the axis means away from the axis. Actually, away from the axis, the field lines will be curved. They'll be, I mean, for a single loop, if you see here itself near the loop, I will draw. There'll be one field line going straight. Other field lines would be like this. Okay, entering from one side and leaving from the other side. But since the point or since the position of L2 is very far from L1, the other field lines also will almost be parallel to this one. Okay, you will not be able to appreciate the curvature anyway at that in that small region. So you can assume L2 is under a uniform magnetic field produced by L1. Okay, so you can say it's like the magnetic field is like this. Consider it as a uniform magnetic field because the region over which the loop L2 is spread is a very small region compared to that distance. Okay. Now, does the field B1 exert any force on elements of the loop B2, L2? And what will be the resultant of the force on all those elements? That's the question. Actually, if you take it as a uniform field, tell me, we already discussed this. What is the net force experienced by a current loop in a uniform magnetic field?
0, sir.
0. Okay, so if you take uniform field, then the answer will be 0. I think we will have to consider the curving of the field lines. It's okay, you can take it like this. Will the second loop experience any net force due to the magnetic field B1? Let's look at it as a separate question. Okay. Consider a loop like this and imagine some field lines. One field line at an angle like this. One field line straight. One field line at an angle like this. We need to check if this current loop can experience any net force due to this non-uniform magnetic field. And how is the current flowing? So you can think of these field lines like a cone actually. In 2D on the screen, it looks like this. But in 3D, if you imagine, the axis becomes the axis of the cone and the field lines would be like going away like this. Okay. So tell me, will the loop experience a force or not? I'll try to help you with the visualization, but think about it. Okay, think of it this way. Assume there are field lines along the, what do you say, slant surface of this cone. And let's say the ring is like this, the loop. Okay, we could have rotated it also. Just a moment. Okay, let's say the field lines are along this cone and the loop is like this, half of it out of the screen and half behind the screen. In the part which is out of the screen, the current is going up. Okay. Let's imagine one field line, say this one. Now at this point, the current is going into your screen. So it's in the Z direction. The magnetic field is inclined at an angle like this, that yellow line. Okay. So tell me, what is the cross product ideal cross B? What is the direction of the cross product ideal cross B for this element, this topmost element? In that topmost element, the current is going into your screen. So ideal is inwards. You can see the magnetic field vector. What is the direction of their cross product? Is it clear to all of you that the current is going into the screen at that point in that element? So place your right hand fingers into the screen, curl them in the direction indicated by that yellow vector. Which way is the thumb pointing? Okay, so you'll need more practice on this
So
also.
can you repeat again what did you say?
See, in that loop, current is flowing upwards. Okay, maybe I should just draw the loop properly. Just a moment. This is the current carrying loop. Okay, so at the topmost point here, current is going into your screen and then it will be coming down behind the screen. So at that point, it is going into the screen and magnetic field is that yellow vector. What is the direction of force on that current element?
Sir, upward. Like,
Upward like this?
yeah.
No. See, ideal cross B, the cross product of two vectors should be perpendicular to both the vectors. So the force must be perpendicular to the magnetic field. It should also be perpendicular to the current element. The magnetic field is inclined at an angle like this. Then if you are saying the force is this way upward, these two will not be perpendicular, no? Force should be perpendicular to magnetic field. Listen, all of you. At the topmost point, the current element is directed into the screen. That is the Z direction. This cross product should be perpendicular to dl and also to magnetic field. dl is in the Z direction. Now, if you want the force to be perpendicular to the current element, force must be perpendicular to Z direction, means it must be in the XY plane. That is in the plane of your screen. Okay. And being in the plane of your screen, it should be perpendicular to magnetic field also, means the force must be this way. Okay, such that this angle is 90 degrees. That way the force dF, the small force on that element, will be perpendicular to the current element and also the magnetic field. So that's the proper direction of ideal cross B. If you want, you can try. Place your right hand fingers into the screen, pointing into the screen, curl them in the direction of that yellow vector. The yellow vector is not exactly to your left, no, it's tilted downwards a little bit. Do that, the thumb will also turn a little bit. Okay, rotate a little bit. So that's the direction of force experienced by that element. Then bottommost element, if you see, it will be experiencing a force this way, dF. So basically different elements experience force in different directions, but we can see that they'll all produce a resultant this way. Okay, so this second loop L2 is going to experience a force of attraction towards L1. Fine. You all could have thought of it this way also. I just asked you, will the loops be attracted or not? And I asked you this question also, what does a current loop behave as? And the answer was it behaves as a magnetic dipole. Now tell me, for the loop L1, which side is north, which side is south? For L1, which side is north and which side is south?
So to the left of L1 is north.
Left is north and right is south. And for L2 also it will be the same. This will be north and this will be south. South, north are close to each other, so they will attract. Okay, so these two will have a force of attraction between them. Are you all convinced or not?
Yes, sir.
Okay, if any of you have any doubt, you can ask. So these two loops are going to attract each other. Okay. You have to find out the force of attraction. But just tell me an idea. I don't want the exact answer, but what can be done? Current is known, radii of the loops are known, and the distance between them is also known. We need to find out the force of attraction between the loops. What can be done? Again, the hint is what a current carrying loop behaves as. Okay, it behaves as a magnetic dipole. So there is one dipole here, okay, directed to the left. You can calculate its dipole moment also, not a big deal. Current multiplied with area, I into pi r square. So we know the dipole moment of this magnet, and we know the dipole moment of that other magnet also, other loop also. Okay, these two are coaxial dipoles having the same orientation, placed at a large distance from each other. We had done a question like this in electric dipoles. Okay, when we calculated force of attraction between two electric dipoles, you can use the same formula here. Whatever formula you get in electrostatics between electric dipoles, you can use the same result here with magnetic dipole moments. Okay, do any of you remember the force of attraction between two coaxial dipoles? I don't even know which lecture we discussed in. Okay, go through it once. Just remember, whatever ideas were discussed around electric dipoles, same ideas can be applied to magnetic dipoles. Only change you will need to make is, in electrostatics, you would have derived the results in terms of K. We know K is 1 by 4 pi epsilon naught. When it comes to magnetism, this changes to mu naught by 4 pi. So in place of K, you will have to write mu naught by 4 pi. And in electrostatics, you would have had dipole moments P1 and P2. When it comes to magnetism, it changes to magnetic dipole moments M1 and M2. Rest of the equation will be the same. Distance x will be distance x. Any other pi 2, any other dimensionless constants, they will be written as it is. Okay, try this later on your own, all of you. Find out the force of attraction between these two dipoles and revise the actual idea also, how we calculated the force of attraction between two coaxial dipoles, okay, separated by a large distance. Fine then. Practice some problems based on this chapter. Tomorrow I'll send you a worksheet also with a few questions. And next class, which will be on Thursday, we will start the next chapter, magnetism and matter. Okay, small chapter, we can finish it off in 1 or 2 classes. Okay, I think now Earth's magnetism is also deleted from the syllabus. So we only have to discuss the types of magnetic materials, relative permeability. Okay, it will be done in 1 or 2 classes, not a big deal. Okay, thank you all. We'll continue on Thursday. If you have any doubts, you can ask. But solve this question properly and send me the answer.